In this video, we focus on computing limits by using the formula for a piecewise defined function. So we're going to look at two examples where we compute left-sided, right-sided, and ordinary limits based on the formula for a piecewise defined function. And then for each example, we'll go ahead and verify by using a graphing utility. So in our first example, we're given this piecewise defined function f of x. And it follows the rule f of x equals 4 plus x when x is less than 0, in other words, negative values of x. But it switches to the rule x minus 2 quantity squared, so f of x equals x minus 2 quantity squared, when x is bigger than or equal to 0. Now we want to compute the one-sided limits at x equals 0, and then the ordinary limit at x equals 0 if it exists. So to get the left-sided limit, the limit as x goes to 0 from the left, in other words, values that are slightly less than 0, we have to use the first rule for f of x, because that's its definition when x is negative. So we're really just computing the limit as x goes to 0 from the left of 4 plus x. And we're not doing anything too formal yet. I can say with confidence that 4 plus x gets very close to 4 when x gets close to 0. So our left-sided limit is just 4. Now in part B, I want the right-sided limit as x goes to 0. And that means the limit as x goes to 0, but x is slightly bigger than 0. That puts us on the second branch of this function, because that's the rule that we follow when x is bigger than 0. So really I'm computing the limit as x goes to 0 of x minus 2 all squared. And I can see that when x is very close to 0 there, this expression is very close to negative 2 squared, which is positive 4. So because my left and right-sided limits agree with each other and they're both equal to 4, we say the ordinary limit exists and that's equal to 4. And I'll post a link to a video at the top where we first discussed this informal definition of ordinary limits. But the idea is if the left and right-sided limits agree for a particular value of x, then the ordinary limit is going to exist and be equal to that same value. Now, before we move along from this example, I want to verify graphically that these limits actually make sense. So we plug into our plotting software and we obtain the graph of f of x. And we're interested in what it's doing near x equals 0. And here's what it's doing. F of x has this little cusp at x equals 0. That's where the switch happens between the two rules that we use, left of 0 and right of 0. And I can see clearly that f of x is getting very close to 4 as x gets close to 0 from both the left and right. And in fact, just as a little bonus here, f of 0 is actually equal to 4, which means the function is continuous at that point. In our next example, we have a piecewise defined function, and it's defined in terms of the trig functions sine x and cosine x. So f of x is going to follow the rule, f of x equals sine x, provided x is less than or equal to pi over 2. But then we switch to the rule f of x equals cosine x if x is bigger than pi over 2. So as we're approaching pi over 2 from the left, that means x is getting close to pi over 2, but x is slightly less than pi over 2, which puts us on the first branch of the function. So f of x is going to be sine of x as we approach this point. So as we're getting close to pi over 2, the sine of x is getting close to the sine of pi over 2, and that's just 1. Now in part B, we approach this point from the right. That means x values that are slightly bigger than pi over 2, which puts us on the cosine branch of this function. So now I have to ask, what is the cosine function getting close to when x gets close to pi over 2? And remember, the cosine of pi over 2 is 0. So this time the left and right limits don't agree with each other, which indicates there's a jump in the function. And the ordinary limit doesn't exist, so we simply write dne for that. And when we bring in a plot of the function, we see that jump discontinuity happening at x equals pi over 2. We're suddenly switching from the sine function to the cosine function, and they don't have the same vertical value at pi over 2, so we get a gap in our function. In our next video, we're going to learn how to approximate limits by using a calculator. In other words, by actually just plugging in values of x that are closer and closer to the point of interest. And this is going to allow us to approximate some limits that are really interesting, where it's just not obvious algebraically what the value of the limit should be. I'll post a link to that video at the upper left, and I'll see you there.